Hello, everyone. So today we're going to be doing a quick crash course into infrared spectroscopy. So really what we're going to be doing here is watching how we can use light to make some molecules do some dancing. So in order to really understand infrared spectroscopy, the first thing we have to really focus on is molecular movement, because that's really what we're going to be examining with this technique. So one of the useful things to remember is that molecules are constantly moving all of the time, both the molecules themselves and their component atoms. And there's a lot of cool information in this molecular movement. And one of the big things, we can usually measure the total amount of this movement by the temperature. So this is one of the reasons why you can never have a molecule that truly gets to 0 degrees Kelvin. It can get really close, but it just can't stop moving. So we can go ahead and look at how all of this movement is embedded in the system using 3 major types of movement. So the first of which is that they can translate. So this is the idea of them moving in the 3 major directions: forwards, backwards, up, and down. So they can run around a room just like anything else. Then we've got rotations. So molecules can typically spin around. So we're not going to be too concerned about either of these movements, but you can actually get a fair bit of information about certain molecules using these. We are going to focus on the third type. So this is the really important one for organic chemistry: vibrations. So that's what we're really looking at on this right-hand side, is the vibrations of a water molecule. So these are essentially how molecules move with respect to each other. So we can see these hydrogen atoms bending up and down, and we can also see these stretches as they're moving out and back. So these stretches can be either in sync or out of sync. So feel free to wave your arms in front of you. That's what water molecule is always doing. So one of the cool things is that it turns out that molecules can absorb light in a very specific part of the electromagnetic spectrum to enhance any of these degrees of motion. So what type of the spectrum will change what type of movement? So one of the ones that we use a lot is rotational, because rotational spectra, rotations absorb in the microwave region. So by hitting a water molecule with microwave radiation, you can make it spin faster, which is what heats up the molecule. However, the one that's a little bit more relevant for us is going to be infrared spectroscopy. So I want you to make note that infrared is going to be slightly higher frequency, but lower wave, higher frequency, but smaller wavelength than the microwave, and both of these are going to, both microwave and infrared are going to be a much lower frequency, but a higher wavelength than infrared. So the big visible spectrum. So this is the light we can see. We're going to be looking at this stuff that is lower frequency, which means that it's going to be lower energy. And that's the big thing I want you to focus on, is that visible light has a lot more energy than infrared. But it doesn't mean that we still can't use some infrared, because this infrared region is going to be the mode at which, if I expose a molecule to infrared, I can speed up these vibrations, which means this is a traditional, very easy way to heat a molecule, because as I speed up these vibrations, they have more movement and they're higher temperature. So if you've heard of things like infrared lamps, or even like the radiation that comes down from the sun, a lot of the heat that we absorb from the sun is through this infrared radiation. So this is what we often feel as warmth from radiating sources, whether they be fires, the sun, or even old incandescent light bulbs. It's mostly coming through this specific region. So it's also worth noting that any warm object will also give off low levels of IR radiation, mostly from vibrations, but from a couple other ways. And so this is why you can often feel something being warm at a distance, even without touching it, is this movement of infrared radiation. And again, the reason why is because all molecules can do some level of infrared absorption depending on what bonds they have. So one of the things that's going to be a little bit weird with infrared spectroscopy is you've probably encountered frequency and wavelength before. But due to some historic reasons of the way it was originally easiest to measure infrared radiation, we use something called wave numbers. So a wave number can really be thought as inverse wavelength. And how you got this is you sent light through a prism, and you'd literally go ahead and see how many times it would interfere or how many peaks you would get over a 1 centimeter length. And so this is the reason we're typically going to measure our infrared radiation in the number of peaks per centimeter. Now, what's useful is this is going to be proportional to frequency. And since wave numbers and frequency are proportional, that means that wave numbers also scales with energy. So the higher the wave number, the more energy is involved in a vibration. So go ahead and I want you to mostly focus on this key feature of wave numbers and energy as we go ahead and talk a little bit more about these IR vibrations. So we're going to take this whole realm of molecular vibrations and split them into some very specific types of movement with their characteristic frequencies. So first thing I want you to know is that the number of vibrations will scale with the size of a molecule. So if you have a nonlinear molecule, so pretty much anything bigger than 2 atoms, it typically has 3n-6 vibrations, where n is the number of atoms. So if I have something like a water molecule, n is 3, and so I have about 3 vibrations. But if I have 4 atoms, I'd have 6 vibrations, and 5 atoms would give me 9 vibrations, and so on and so forth. So we're going to have a lot more vibrations as I get to larger and larger molecules. But due to some peculiarities of how vibrations work, not all of these vibrations will be observable. So we're going to be focusing in, we'll only see a subset when we do infrared spectroscopy, which is very nice. Otherwise, there'd be a few too many for us to look at. Now we're going to take these vibrations and split them first into 2 main classes. So the first of which are going to be these bends. So this is where I've got these atoms bending either towards or away from each other. So they're bending back and forth. And these are fairly low energy vibrations. So these typically occur somewhere in between 500 and 1500 centimeters. So note that water with a bend around 1600 is pretty high energy for a bend. So most of the values are going to be much lower than this. And these ones are going to be often hard to kind of categorize. So we'll only use 1 or 2 bends, and I'll mention them very infrequently. Many scientists who are well experienced using infrared spectroscopy can get a lot more information out of bends, but we're going to be focusing in on the much more useful part of the spectra. These are going to be the stretches. So this is how those atoms, how each of our bonds stretch forwards and back. And it's worth noting that some of these stretches can be coupled. So notice how we aren't looking at a single hydrogen-oxygen stretch in either of these water ones. They'll stretch, they'll often be paired in what are these called these asymmetric or symmetric stretches. Not too important, but worth noting that you will have a lot of these stretches can get a little bit more complicated. Now, the important thing to note here is that the stretches typically occur in between the 1,000 and 4,000 inverse centimeter region. So this is a region we're going to care a lot more about when we're doing spectroscopy, because these stretches are a little bit easier to use to identify a molecule. So let's go ahead and take a look at what a IR spectra looks like. So another peculiarity about the IR spectra is, unlike UV vis, where we use absorbance, in infrared, we're using percent transmittance. That means that if I have, so this is how much light makes it through the sample. So that means if I have no sample, I'd have more or less a relatively flat line going right through 100. So the more absorption I have, the lower the peak is. So we're really going to be reading our peaks from top to bottom. And each of these peaks tends to correspond to a specific vibration or sometimes set of vibrations with unique frequencies. And so we're looking at, again, the amount of light being transmitted through the sample and the major frequencies at which they absorb light. So it's worth noting that most of our vibrations tend to have fairly narrow regions, but you're going to see some groups that have a lot of strong intermolecular forces, so they interact very strongly with other molecules, will experience much broader peaks. And so that's really what we're seeing here with water. Water typically has these two relatively broad and fairly strong peaks, which makes sense because water spends a lot of time interacting with water. So I want you to be very cautious when you're doing IR spectroscopy, because if you tend to have a significant amount of water in your sample, you may end up seeing these two major peaks. So I want you to be cautious of those because they can interfere with the sample. So we're going to assume that most of your samples are either going to be relatively pure or have some sort of organic solvent, which shouldn't cause too much of an issue. So what we're going to do is we're going to go ahead and take our big spectra, which again goes all the way from 0 to 4,000 inverse centimeters. So this is our IR region, and we're going to split it up based on the major types of vibrations and what types of bonds are being vibrated at that point. So again, we're mostly going to be focusing in on bond stretches. So that's that region above 1,000. However, you do get some bending modes in this 1,000 to 1,500 region. So most of our focus is going to be about 1,400 inverse centimeters and above. So again, 1,400 centimeters and to the left, because again, the left is going to be higher numbers in infrared spectroscopy. So we're going to use this region to help us identify major types of functional groups that might be present. So again, one of the things we're going to note is lower energy stretches are typically going to correspond to single bonds. So this is going to be things like carbon-carbon, carbon-oxygen. Double bonds, such as CO and CC bonds, are going to be in this 15 to 2,000 region. Triple bonds are going to be in between 2,000 and 2,500. Now, above 2,500, this is going to be a good region for organic chemistry. This is going to be bonds involving hydrogen. And so what we can do is we can use a set of tables that tell us exactly at what frequency we'd expect any given functional group to show up. And some of these have very characteristic intensities. So as I said previously, oxygen-hydrogen bonds tend to be very broad and very strong. Other bonds, such as alkene-hydrogen bonds, can be a little bit weaker. So that means they don't go as far. So a lot of our focus is going to be split into two major regions. So first, we're going to be looking at our groups containing hydrogen. So this is our OH, NH, and CH bonds. So these almost all occur at some frequency above 2,700. So again, this 2,700 to 3,700 inverse centimeter region. So again, each one of these functional groups will have a slightly different frequency. And then we've got all of our vibrations that include second row elements. So where we don't have any hydrogen, it's just mostly going to be carbon, nitrogen, and oxygen. These are all going to occur relatively below 2,700 inverse centimeters. And again, we're mostly looking just at the stretches. Now, one of the things I want you to note is because we are going to be looking at a lot of organic molecules, this means that we're going to have a lot of carbon-hydrogen bonds. So expect a lot of peaks in that 28 to 38 inverse centimeter, 28 to 3,000 inverse centimeter region, because we're going to have a lot of those. We're also going to have a fair bit of absorption in the carbon-carbon bond region. So let's go ahead and take a look at what an organic molecule looks like without any functional groups. So hexane is a pretty good example. So if I'm looking at hexane, one of the first groups I expect to see a lot of is these CH stretches. So you may see here, we have a lot of these carbon-hydrogen bonds moving in sequence, each bond stretching or contracting in alternation. So these sort of CH stretches are going to occur really readily in this 2,800 to 3,000 region. So you're going to tend to see a lot of these in a lot of your spectra. The other major bond type of vibrations we're going to see are in this 1,200. So kind of this 1,000 to 1,300 region, where you're going to see these carbon-carbon stretches. So our carbon-carbon bonds are going to elongate and contract. And so these are going to be present in most of your spectra. Again, worth noting, we still see a lot of these bends occurring below the 1100 region, so we're not going to pay too much attention to these. So expect to see these basic peaks in most of your IR spectra. Now that you are aware of them, more or less make note. Most of the time we could ignore. Special attention should only be really paid if you see them absent. If these are absent, it will often tell you that something a little bit interesting is happening. Now, let's go ahead and focus on some of our major functional groups. So this is one we've seen before, oxygen. So alcohol groups, OH bonds, these are going to cause a couple additional peaks as I start adding in my functional groups. So for example, as we saw before, OH bonds, they tend to have these very high energy stretches. So these occur in between the 32 and 3600 region. Note that they're very broad. This is also one of the reasons why you have to pay attention to whether or not you have water in your sample, because note this can look a little bit like water for a reason. But again, this sort of broad spectrum, which is fairly intense, is a good indication you probably have an alcohol present. Note that this is often coupled with a strong stretch around the 1000 region. So again, down here in this low region. Now, one of the last things I want you to note is that this is probably one of the highest energy bends you'll see. There is a carbon-oxygen bend that occurs around the 1400 region. But note, this is the same region where we tend to have our carbon-carbon bonds. So as a result, you can usually only see this in terms of some broadening. So don't worry too much if you see it or don't see it. It's just worth it noting it may occur. Big focus here. First thing you're looking for is this OH stretch. If you think that's an alcohol, go ahead and just confirm that you have some sort of peak down around 1000. It's probably a good indication you have an alcohol present. Now, another major type of functional group we have in a lot of organic molecules are going to be our alkenes and alkynes. I'm specifically going to be looking at the alkenes. So if I've got a carbon-carbon bond, it's going to take a little double bond. This is going to take a lot more energy to vibrate than, say, a single bond. So as a result, it's going to occur at a higher wave number. So for example, here we have a carbon-carbon single bond around 1400. The CC double bond stretch now occurring near around 650. So again, most of these carbon-carbon double bonds are going to be somewhere in this 600 region, 1620 to 1680. And again, this is that double bond stretching and contracting. Now, worth noting, a lot of times these alkenes are going to have hydrogen atoms attached to them. So when I have a hydrogen atom attached to a double bond or an alkene, this is going to have a different vibration than if it's attached just to an alkane or an sp3 carbon. So these ones are also going to be a little bit harder to stretch than normal. So we're going to see an absorption above 3000. Now that's the important thing I want you to pay attention to, is if you see an absorption band above 3000, that usually indicates the presence of a double or triple bond. In this case, we have this nice absorption around 31. It's a pretty good indication when you pair it with this double bond stretch that I've got an alkene present. So again, I have an alkene with hydrogen atoms attached. So this gives me a good indication of at least what sort of functional groups are present in my atom or my molecule. Now, worth noting is that not all double bonds are going to be created equal. Something to pay attention to is that you're going to have slightly different absorptions, whether you're looking at an alkene or an aromatic. Because when I'm looking at an aromatic molecule, you'll note that I'm going to be alternating these double and single bonds. So my peaks are going to be somewhere in between those double and single bond peaks. So typically, these are going to occur in between that 14 and 1600 region. So you'll often find them stretched out in between 1450 and 1550 when looking at these carbon-carbon stretches. However, again, most of my aromatic molecules are going to contain some hydrogen atoms. So we're also going to see these CH stretches. These are often going to occur in a very similar region as our alkene hydrogen bonds. So again, this 3000, 3100 region. So based on the hydrogens alone, it would be hard to tell the difference between an alkene and an aromatic. And that's why using these double bonds can really, the aromatic double bonds can really help you out. Another important thing to worth noting is that aromatics, by their nature, involve at least 6 carbons and often involve many hydrogens. So as a result, these peaks often occur in clusters where I'm going to have multiple carbon-carbon bond stretches and multiple carbon-hydrogen stretches. For more complex molecules, you may see more or less of these bonds depending on how light can be absorbed through the molecule. But if you're seeing frequent number stretches, again, especially paired with location, start thinking a little bit more aromatic or multiple alkenes. Now, one of the big foundational or functional groups is going to be our carbonyls. So carbonyls tend to find fairly strong absorptions in this 1650 to 1850 region. So again, just above our double bonds or our alkene bonds. And they often tend to be fairly intense and relatively sharp. So again, this is that stretching and contracting of that carbon-oxygen double bond. Now, the tricky bit of the carbonyls is they occur in multiple different types of functional groups. So depending on the functional group, this peak might be slightly shifted. So, for example, if I'm looking at ketones, this tends to occur a little bit more on the lower range and between 1680 and 1750. However, note that most of the other groups are still going to be in this range. So if you're looking at a carbonyl, which we clearly have here, you need to start looking to see if you can find any characters of a different type of carbonyl functional group besides a ketone to make sure you can eliminate those. So a good place to start is the aldehydes. So if I've got an aldehyde, in addition to this nice carbonyl stretch, again, in that 1680 to 1750 region, so the same exact region as a ketone, I'm going to see a CH stretch. Now, a cool feature of the aldehyde CH stretch is they always come in pairs. So these tend to have double absorptions in the 1750 and 2850 region. This is referred to as what I love to call the aldehyde fangs. Now, worth noting, sometimes the fangs are going to be a little bit more pronounced, and sometimes they're going to hide a little bit better. However, one of the major reasons why is that this peak at the slightly higher wave numbers or slightly higher energy often can hide in that bigger mass of carbon-hydrogen peaks. But you're usually going to see that peak that's closer to the 17 to 1800 region. That one tends to be a little bit more visible. And so that's a good indication that you've got an aldehyde, again, when paired with that carbonyl, because you can't have an aldehyde without both the CH and the CO stretch. So look for both of them at once. Now, another major type of carbonyl functional group is going to be our carboxylic acid. So in this case, we're going to have our CO double bond stretch, again, in that same carbonyl region. This one tends to be a little bit higher in the 1700, 1750 region, so a little bit higher energy. The big distinguishing feature of the carbonyl is going to be that OH bond. So these tend to be very broad. And so as you see here, they can go all the way up to about 3600 and down to about 2200 inverse centimeters. Now, this often makes it very easy to identify that you have a carboxylic acid, because note that the alcohols tend to be more centered around 33. So this is a little bit lower frequency or wave number, in addition to being a much more broad. So it's easy to identify if a carboxylic acid is present. The problem here is that it's often very difficult to obtain any information about any of the other CH or OH coordinations because it's so intense and so broad. Because again, more broader spectrum are often deal with molecules that have good intermolecular forces, and that hydrogen wants to go places. Now, let's go ahead and take a look at what real molecules look like. So far I've been looking at molecules that mostly have one, or depending on how you count it, combining an OH with a carbonyl, 2 functional groups. Real molecules will often have much more. So this can lead to a lot more complex spectra, and so you have to keep an eye on multiple regions and figure out how they coordinate. So for example, if I'm looking at benzaldehyde here, I'm going to be looking at 4 key regions. So first thing that should really stand out to you is that we have a very intense peak around 1700, but also note that we have any absorption above 3000, an absorption a little bit below 2700, and we definitely have some action going around 1400. So let's go ahead and look at what all of these together examine. So first thing that I like to go to is note we have an absorption above 3000. This immediately means I have some sort of carbon double bond. By, by looking at the double bond region, I note that I don't really have any peaks around 1600, but I have one just below 15. This is a good indication that I've got an aromatic group. I definitely have some double bonds. They're not full double bonds. This is classic aromatic. Now, this leads our other 2 major peaks. So I definitely have a carbonyl. That is a beautiful, strong peak around 1700. But what type of carbonyl? Well, I obviously don't have a carboxylic acid. I could have an ester. I could have a ketone. But big thing here, look at those nice, pretty aldehyde fangs. That absorption around 2700, good indication that I've got, confirmed the other tooth, an aldehyde fang. So this is a good indication that in addition to this carbonyl vibration, I also have an aldehyde. So at the very least, I know that I have an aldehyde and an aromatic. One of the things that's also worth noting what you don't have, note that I don't have a lot of absorptions in this 1000 to 1400 region. So I don't have a lot of essentially alkane carbons. Not a lot there, not enough definitive, but that would indeed agree with a benzaldehyde. So again, you may note that this IR is a very good confirmation technique of what you expect. It can also let you know if something got in that you weren't expecting in case you see any unexpected peaks. Now, one of the things that's worth noting is I went ahead and I just hit some of the major functional groups. So again, worth noting, you also have a couple others I didn't talk too much about. Esters, these are going to be relatively similar. Relatively similar to ketones. They just might have an extra small peak around 1000. And I've also skipped over nitrogens and alkynes. So again, alkyne, big thing to there, look for a peak around 2000. And nitrogens, we're not going to go ahead and deal with until we hit them in class. But one of the big things is that you can go ahead and use your IR spectra in 2 major ways. So the first, and this is a big one, is if you're given an IR spectra, first thing you should do is go ahead and tick off what functional groups are going to be present. This will often give you a good starting place of guessing what molecules you made. Sometimes it can also be important of checking off what functional groups are not present. Now, one of the other things you can do, and this is what we're going to typically do in lab, we'll often have an idea of what molecule I did generate. What you can do is use these peaks to verify that you produce the desired product and that you didn't accidentally produce something else. So if you expect that we're, so when we're making our, working with vanillin, we're going to expect that we're going to have some aldehydes and some aromatic groups. So make sure that those are present. And again, if you don't think you're making an acid, make sure you don't have an acid peak. And this can apply for any of the functional groups. So I'll go ahead and I'll try and produce a quick video where we can go ahead and apply some of this problem solving. Till then, take care.